Chapter 2 is on atoms, molecules, and ions. In this chapter, we will learn about the structure of atoms, which particular elements exist in a molecular form, so in that case, they're diatomic, and then we'll talk about ions as well. We will also learn nomenclature of covalent as well as ionic compounds, hydrates, and a little bit about balancing of equations. It all stems back to Dalton's theory. So, Dalton is considered the father of the structure of atom, and even though none of his postulates are acceptable right now as of modern current day atomic theory, but he was the one who started it all and made a couple observations that led others to follow, and make more significant discoveries. So the first thing that he said was that elements are made up of tiny particles, and these are called atoms. And he called these atoms as indivisible units. That means the most basic unit of any material object is an atom, and atoms cannot be divided into anything else. Of course, now we know that atoms contain electrons and protons and neutrons, and upon a fission reaction, for example, you can actually break an atom into other particles. So that particular postulate was proven wrong. He also said that each element is characterized by the mass of its atoms. So, according to Dalton, what he is saying is that gold is different from silver because gold weighs differently. And what he suggested was that atoms of the same element, they will have the same mass, and atoms of different elements will have different masses. And we now know that that's not true. Atoms are actually characterized by the number of protons that they have, which is also called as the atomic number. And so in that sense, one can say, for instance, that carbon, it's going to contain 6 protons and 6 neutrons. There can be another form of carbon, and I'm going to say that that element, that particular atom, is a form of carbon and not nitrogen, let's say, because it contains the same number of protons and it contains different number of neutrons. So when neutrons are different, the top number, which is also referred to as the mass number, we'll talk about that in a little bit, that changes, whereas realize the bottom number, which is the atomic number, remains the same. And so for that matter, one can say that these two, the C12 and C14, they are the isotopes of a given element. The third thing that he said was that chemical reactions only rearrange in a way, the way the atoms are combined. That means the atoms themselves go unchanged. Of course, now we know that when a chemical reaction takes place, whether it's going through an ionic reaction or, you know, an organic reaction, so whether sharing of electrons occurs or transfer of electrons occurs, there is actually a material particle that gets exchanged. And for that reason, chemical reactions are not just a rearrangement of atoms, but an actual transfer of a material particle. And in this case, that happens to be an electron. So first things first, I want to take some time to talk about some of the material particles, and the first one we'll talk about in this course is the electron. The other two that we'll discuss would be the protons and the neutrons. So electron was discovered by the very famous cathode ray tube, that experiment which was done by a British physicist by the name Thomson. And what he did was he took a cathode ray tube, and then he coated the inner walls of that with zinc sulfide. So it's a phosphorescent compound, he took zinc sulfide, so he coated the internal walls of this tube. He basically removed the entire air that was present, and then he filled this with a specific gas. He connected this to an electrical field, and what he noticed was a glow in the middle of the tube. And he was kind of puzzled, and he was wondering what that glow, or where that glow rather, where did that come from? And so, in order to figure out whether it was the source of, whether the source of that glow was the components themselves or what. And so what he did was that he switched from a specific gas that he began with. Let's say he took oxygen first, he switched that to a nitrogen, to a neon, to air. All of them continued to show this glow. And so, what does that tell you? That should tell you that this property is present in anything which belongs to the physical world, which is why any and every gas that he was using, he was getting the same answer each time. Now, the other thing that he figured was basically he wanted to check whether there is charge associated with this glow. And so what he did was he set up this entire experiment. He set that up in presence of an electrical field. So what he saw was that as he brought a negative charge close to this tube, so the negative charge, when that was brought close to the tube, essentially the glow got deflected away from the negative charge towards the positive charge. What does that tell you? That should tell you that whatever this glow comprises of, that does contain something that's negatively charged. And other experimenters, other scientists later on used this work in addition to some other information that was given to determine the charge to mass ratio of an electron. Now, it is important to note that the deflection of the electron that they saw in presence of the magnetic field and the electric field did depend on the strength of the electric field. So that's an important point there. And of course, this deflection would also be dependent on the amount of negative charge on the electron and the mass of the electron. So, based on Thomson's work, essentially, he was able to calculate like a charge to mass ratio of 1.75 times 10 to the 8th coulombs per gram. So, if you think about these results, you can perhaps envision that irrespective of the kind of gas that he filled that discharge tube with, he always saw the presence of this glow. And that's indicative of the fact that whatever this particle was, essentially it was present in any and every kind of material. So it's kind of universal. Another thing to think about is since it got deflected in a direction that, let's say you have a discharge tube and you have a positive plate and you have a negative plate, essentially it moved away from the negative and towards the positive. So that's again indicative of a negative charge. And like I said, the strength of the field was pertinent. In absence of field, basically you would see that this would go in a straight line. And so these were independent of that composition from which they originated. So they carried a negative charge, and so hopefully you can see that since the electron itself had a negative charge and material around us is neutral, that means there has to be some kind of a positive charge within the structure of an atom. So Thomson actually, there are two pretty big important things that you can think about his work. One is that before his work, people thought that an atom was essentially indestructible, but now it was obvious that the indestructible atom could apparently be chipped, and it could at least be divided into electron and something which is positive, which could be as a particle or could be a diffused mass. So what Thomson suggested was what is also referred to as the plum pudding model. And what he said was that the positive charge is kind of like a gigantic sphere, and the negative charge is embedded within it pretty much the same way as would plums in pudding. And so that's why the analogy. Um, as we will go forward, you will see that this model was discarded based on several experiments that were done by Rutherford. But before we get to that, I would like to talk about another scientist by the name Millikan, who was an American chemist, and he ran his very famous Millikan's oil drop experiment and determined the charge of the electron. And so, since the charge of the electron was figured out by Millikan, the charge to mass ratio was given by Thomson. Essentially, we were able to determine the mass of an electron as well. So what Millikan did was the following. He sprayed oil into fine droplets using like an atomizer, and these droplets were basically allowed to fall under the influence of gravity through a small hole, um, and those were then viewed with the aid of a light source, like a microscope. And during their fall, the drops basically acquired a charge that was produced by bombarding the air in the chamber with ionizing radiation. So this is what I'm showing you here, like a cross section of what was going on inside um, his experiment. So here is where we have the spray. So a fine mist, fine droplets are generated, and that's the pinhole through which one drop at a time will be allowed to fall down. Realize that the two plates are charged with a positive charge on the top plate and a negative charge at the bottom. And as the drops are falling, essentially they are going to be ionized using X-rays. And so they are going to acquire a negative charge as well. And so hopefully you can see that the gravity would allow the drop to fall down, whereas the negative charge is going to cause a repulsion. So the rate at which the drop is going to fall would or could be measured, because it will become very slow. There is an electrostatic or electronic repulsion force, and there is gravity, both of those together, and you would be able to measure some rates, and that's what Millikan did as well. So by basically measuring the size of the electric field that was required for halting this free fall, and figuring out the masses of the droplets themselves by determining the radii, the density, all of that good stuff, Millikan was basically able to calculate the charge of each drop. And since he said that each drop basically is, since it has been ionized by the X-ray, the amount of charge that it's going to carry is going to be the whole number multiple of the amount of charge that an electron carries. And indeed, he found out the charge to be 1.60 times 10 to the power of negative 19 coulombs. And of course, Thomson's work of the mass to charge ratio for the electrons was given as 1.76 times 10 to the power of 8. So putting the pieces together, essentially the mass of an electron was determined to be 9.1 times 10 to the negative 28 grams. That's tiny. That's very, very small. And so, one of Thomson's deductions that the mass of an electron is about 1 over 2,000 times lighter than the mass of hydrogen atom, which is also the lightest atom, ultimately came out true because that number was found to be 1 over 1839. So mass of um, electron is 1 over 1839 mass of a hydrogen atom. It's really, really small. Now, some people might think, why is it that scientists had to work so hard and they had to figure out ultimately, why is it important to measure the charge of an electron? And the answer to that is because electrons are fundamental building blocks of material. They are present in any and everything around us. Recall Thomson's experiment where whether he used air, which is a mixture of gases, or he chose helium or nitrogen or whatever he put, he did see that glow. Scientists really want to know the properties, and one of the properties would be charge. And the magnitude of the charge that is present on an electron is important because that will tell us how strongly those electrons would be held in an atom. And if the electrons are held really strongly, then bonding would basically not be possible. And if bonding is not possible, then maybe compounds would not get generated. And life as we know of today may not have been possible because if there's no bonding, there's no molecules, the DNA and proteins would be missing. So if you think about it, the basis of all, life around you and the way things are kind of flows back, it goes back to the physical properties of an electron, something as little as an electron. So little things sometimes do have big amplified effects. It's important to realize that. Now that the electron was discovered, it was a negatively charged particle, it was a very tiny particle, and so there were several questions that were going around. Since atoms are neutral in terms of charge, and we have discovered something which is negatively charged, it automatically means that there should be something positive. And like I told you, Thomson basically suggested his plum pudding model. And while it was popular at the time, it was proven wrong by J.J. Thomson's work, and you'll see in a second why that happened. What J.J. Thomson did was the following. He basically took a gold foil, so right here you're seeing a gold foil, and he irradiated that gold foil using alpha particles which were kept in a lead block. Realized that the discovery of radioactivity, which basically means it refers to the emission of small energetic particles from the core of unstable atoms. This work that was done by Becquerel and Curie, for which they even got the Nobel award, the Nobel Prize. So at the end of 19th century, they had basically set up that the fact that the structure of atom could be probed that way. And at this time, or by this time, scientists had identified the alpha particles, the beta particles, and the gamma particles. And alpha particles are nothing but helium nuclei, so they are positively charged. And Rutherford, who had worked under Thomson, he was okay with the plum pudding model, but he wanted to confirm that. And in an attempt to do so, he basically employed these alpha particles, which are radioactive, which is why we have put that in a lead block to absorb any additional emission. And so when these alpha particles hit the gold foil, and then how they would behave, that was described, that was studied using this phosphor screen. Basically, what was seen was that most of the particles went through the gold foil and they kind of remain untouched. What that tells us is that essentially most of the space in the structure of atom should remain empty, and that is the reason why the particles get deflected. Some of the particles were seen to go through some kind of deflection, and that would just basically correlate how far away they would be from anything which holds a positive charge. And some 1 in like 180,000 were such that got deflected back. That means they came in and then they got deflected back completely. What that tells you, what that shows, is that there's a possibility that it might have hit a really small region, um, where the charge, the positive charge, is concentrated. And we are saying so because the alpha particles are positively charged. So only if a positive charge hits another positive charge would you imagine, would you think that it should deflect back and repel to that extent. So you have to envision that this last one means that it would have hit essentially a core central portion, perhaps, where the positive charge was aggregated. So this itself kind of proves Thomson's plum pudding model wrong, because now we are saying that our positive charge is concentrated rather than diffused, and that kind of took away from Thomson's work, and scientists realized that this was the more accurate method, and that was then later on adopted. However, what you need to keep in mind is that while we do have a positive end, while we do have a negative end through protons and electrons within the structure, there was one thing which was still sort of incomplete. And if one thinks about, for instance, hydrogen and compare it to helium, hydrogen, hydrogen that has basically one proton. Helium, on the other hand, contains two protons, but the mass of hydrogen is one-fourth the mass of helium. Why is that? Later work that was done by Rutherford and his student Chadwick discovered and demonstrated that unaccounted mass is due to a neutral particle called as neutron, and that explains uh, the discrepancy between the masses of hydrogen and helium, which was the first one studied, and essentially it gives us information that this happens because the mass of a neutron is very similar to mass of a proton. The only difference there being that the neutron will not hold any charge. So just to recap, what did Rutherford do? Rutherford's work basically helped in the discovery of nucleus. What he did was he took uh, helium nuclei. Those are heavy positively charged particles, sometimes also referred to as alpha particles. So helium nuclei means 2 and 4. And these, since they were radioactive, they were put in a block, and only a little hole was made using which it would hit a gold foil. Gold is heavy as well, and the idea being that whatever happens to gold, it is going to be recorded against a phosphor screen and go from there. And they saw that most of the particles remained undeflected, indicative of empty space. Some got deflected to the extent of 60%, and that shows you that there could be a positive center, and one in, really a big number, 1 in a million would be one that got deflected, and that is indicative of the fact that that particular position should have a very strong positive charge, because only then the helium nucleus will have the capability to go through a complete 180 degrees deflection. So if I were to compare the size of an electron to the size of the nucleus, a nucleus is typically written in, it's shown in femtometers, femtometers, and femtometers is nothing but 10 to the power of minus 15 meters. It's really tiny, itty bitty. And if you compare, let's say in layman terminology, if you compare the size of the nucleus to the size of an atom, well, the nucleus is really tiny, small. Um, that number is going to be to the extent of 10,000 or higher, depending on the element. But you're looking at femtometer for the nucleus and angstrom or nanometers the for the atom itself. So hopefully, everybody realizes that the nucleus is positively charged. There are only two protons in there, protons and neutrons, for your class, for the level of your class. And overall, the atom, unless you show a charge on that, that will remain neutral. So whatever is the positive charge due to protons, same as the number of electrons, and that makes a full neutral atom. Okay, let's now talk about the periodic table. As you perhaps can recall from your school or an intro to chemistry class, periodic table is an array, it's an arrangement of all the elements put together according to what is called as their periodicity. Periodicity. What that means is that in this table you would have certain elements which would have very similar properties, and so every eighth element for that matter, so lithium, sodium, and then past that potassium, and then you have an 18 element break. So all of these are going to possess similar properties, and they do. If you think about the softness, if you think about the way they look, and also their chemical properties as to how they react. Let's say you were thinking about the reaction between sodium and chlorine. So sodium is group 1, it has one positive charge. Chlorine is group 7, requires one electron, that's one negative charge. And so when you write down the formula, it's going to be NaCl. Likewise, if you think about potassium and chlorine, it's KCl, rubidium, RbCl. So even their formulas, the way they react with other elements is going to be very similar. So periodicity is essentially the similarity in physical properties and chemical properties, the way they react, the way they behave overall. And hence they are put together in one group. So realize that you have vertical groups. Sometimes they are also referred to as families, or groups. And they are put together in that group because they have similarities in in their properties. Likewise, you can also have horizontal periods. So these are all horizontal periods. And a grid that you get, which is the way we have over here, that is what is referred to as the periodic table. So overall, we will have 7 horizontal rows and we have 18 vertical columns based on the similarity of the properties. So overall, you can divide your periodic table in different groups, and I'm going to talk about each of the groups in a second. Now, one thing that I want to get your attention to is that if you look in this region, essentially, notice this ladder-like structure. The elements that are on the side of that, so boron, silicon, arsenic, germanium, antimony, these ones right over here. These ones, they are what are called as semi-metals or metalloids. Semi-metals or metalloids. And we do so because they share properties for both nonmetals as well as metals. Um, on the left hand side of that ladder like spot on the periodic table, we have all the metals. So these are all metals. On the right hand side, we have all the nonmetals. Other than this last group, which is also referred to as the inert gases or the noble gases. Inert or noble gases. Now, as you can see, that majority of my periodic table contains metals. There are very few non-metals. So, in terms of which group is where, let's take a look at each of these. The group 1, which is the sodium family, that is also referred to as the alkali metals. And the reason that's done, the word alkali comes from an Arabic word to mean base, that these upon reaction with water will generate bases, and hence they are called as alkali metals. The second one, which is the magnesium, beryllium, that family, that's also referred to as alkaline earth metals. These typically are less reactive as compared to the corresponding sodium family, but they are along the same lines of reaction. So these are pretty metallic in nature. So before I go further on, when I say pretty metallic in nature, what comes to your mind? What are metals? What kind of properties do they share? Well, for you to be able to classify anything as a metal, physically speaking, it must have a property of being ductile and malleable. Malleable means that you would be able to beat it into sheets. Beat into sheets. Ductile means that you would be able to draw it into wires. And in addition to that, all metals will have a property of being good conductors of heat and electricity because they do have mobile electrons. And finally, all metals at some point of time should be able to lose electrons significantly easily. They don't typically like to gain electrons. On the other hand, nonmetals would like to gain electrons. They typically do not have a shine or luster. They do not have a specific shape. A lot of them are gases. However, there are some solids and liquids as well. Among metals, you basically have pretty much all of them are metallic in nature, other than mercury, which is a very highly dense liquid. Other than that, metals are all solids. Non-metals could be solids, liquids, or gases. Okay, so now let's talk about, having given you some more information about metals. If you think about this blue kind of sandwiched area right over here, this is what is also referred to as the D block element. And within that D block, we have, if you notice, we have lanthanum, which we have put an asterisk on, and that's 57. And past that, you're supposed to read the 58 all the way to through 71. And then for actinium, which is 89, and then thorium all the way, we have at 103, which is lawrencium, and it is a synthetic element, which is why it has been written in gray. But anyway, those form the actinide series. So together, the lanthanide and the actinide series, they make up what is called as the F block. And most of your synthetic elements, or radioactive elements, they would be found in the F block. The newly synthetic elements that have been discovered recently are also a part of the lower part of the periodic table, rather than high up above that is already known. Um, Within the right hand side of the periodic table, we have what is called as the p block elements, and that just basically means that the electrons are filling up in such a manner that a p orbital will be included, and we'll talk about that in future in a lot more detail. But realize, when you're looking at fluorine and its group, essentially that group is referred to as halogens: oxygen, sulfur, selenium, tellurium. So that is group 6. That one was referred to as chalcogens. That's not written over here, so I'm going to just kind of mention chalcogens. That's the oxygen family. Nitrogen family is referred to as pnictogens. Pnictogens. And talked about majority of the others. All right. Let's take a look what kind of information a periodic table gives us and what can we derive off of that. Recall I told you, when we first started the discussion, the Dalton's atomic theory suggests, Dalton, the first person who talked about atoms, he suggested that atoms differed from each other because they differed in the number of, they were different from each other in terms of the mass. But notice, essentially, the periodic table is increasing. It's in the increasing order of the atomic number or the number of protons. So the way you identify one element from the other, what's unique about an element is its number of protons, or the atomic number. So number of protons and atomic number means the same thing, which is this full whole number that's written on top. I have another picture that I want to show you, and that's right over here. So each of these cells, each of this tablet for every element, it gives us a certain amount of information. The whole number that you see, that is the atomic number. Typically, it's going to be denoted by Z, and it will be a whole number. It's a whole number. On the other hand, the lower number that you see, that's an atomic mass, typically denoted by a capital A, and is a fraction. So the fraction or the decimal that you are seeing, that is atomic mass. The atomic number, or the number of protons, that is a whole number, because of course it's a number. And of course in the middle you have the symbol. Notice the first couple members of the periodic table, they have single letter, and pretty much all at the bottom they have two letters. And this kind of stems back to the fact in the beginning, when only a handful of elements were known. They said, carbon, let's just abbreviate, rather than writing carbon the whole time. Let's just abbreviate that to C. And then later on, there were other elements, such as chlorine or cobalt or chromium or calcium or copper, which started to be discovered. And so now they had to come up with a way to be able to distinguish those from carbon. Not all of those could be C. So then they started laying emphasis on the second sound that kind of is a powerful sound in the name. So for example, chlorine has a L sound, and so the Cl, that's how it came up. Copper comes from cuprum. The Cu is for cuprum, which is the Latin name. So Latin names are the ones that they went for. So for instance, Na is natrium for sodium. So these are all Latin names that they went with. All right, let's talk about writing the standard format of any element. Now, what I showed you from the periodic table in the last slide, that was the information that is given, that is available straight from the periodic table. But that's not standard format. Typically, you would see an element written in its standard format, including the symbol of the element, the number of protons that it has, and if it's a neutral atom, that would mean that the number of protons or electrons, that would be the same. And there will be a top number which will also be a mass number, and that is nothing but the number of protons and neutrons put together, which is referred to as the mass number. A lot of people think that the number written on top is the atomic mass, and that's not true. The number written on top is a mass number, which is nothing but the number of protons and neutrons put together. Often we would find that the mass number, our atomic and the atomic mass are very similar. So in other words, the mass number is a rounded number that you get for atomic mass. So that's the closest relationship between the two. But this number is not atomic mass. It's a mass number, which is a number of protons plus number of neutrons. That means by writing any standard format, you should be able to determine the number of protons, the number of electrons, and the number of neutrons that are present for that chemical species. So realize the difference between that. But if you're just given a periodic table and not much is mentioned about the mass number, then you will need to sort of approximate that, because atomic mass is approximately equal to the mass number. You can round it up or round it down. So for instance, notice that the mass number, or the number of protons and neutrons from the standard format for carbon, is 12. The atomic mass is 12.011, and so when you round it down, you do get 12. So why is it 12.011? Realize that atomic mass is going to include the protons, the neutrons, as well as the electrons. And we learned about it that electrons are really, really, really tiny, tiny masses. So it's not going to add a whole lot. Also realize that this number, even though the units are not written here, it really is atomic mass units, or AMU. Sometimes also just written as U, or Daltons. And it's nothing but a relative scale, because recall that the mass of each proton is to the tune of 10 to the power of like negative 27 kilograms or so. And so rather than having to say that in grams or kilograms, we have established a relationship between the kilograms and a new relative scale, and so these are expressed in the AMUs or U's for that matter.